Thank you all for coming to CSE 132C Database System Implementation. My name is Arun Kumar, and today we have a guest speaker from industry, Andrew Lamb. He is at InfluxData, and he's also part of the Apache Arrow community. And if you have not been following, Apache Arrow has been revolutionizing the landscape of systems for data systems and data management and data science. And it's a huge open source project. And Andrew is a major contributor to it. And so he has worked extensively, not only on Apache Arrow, but also in the database industry and at machine learning startups before. So it's an interesting eclectic background. So happy to have you with us, Andrew, and feel free to take it away. Just a protocol note to the audience, if you have a question for Andrew, please raise your hand and I will pause and ask questions. So Andrew, would you prefer questions during the talk or at the end?
Yeah, I think during would be great. I like, yeah, it'd be good.
Excellent. So I will allow you to pause and ask for questions, or also I will pause at an opportune time if I see questions on the participants list or on the chat.
Yeah, I'd appreciate if you monitored whatever's chat, like I'll be focused on the slides, and if there's something that comes up, by all means, stop me in. Yeah, that'd be great.
Sounds good. Take it away. Thank you, Andrew.
All right. Thank you very much, Professor Kumar. Can everyone see my screen? Hopefully.
Yes.
This is always, it's always kind of weird to do Zoom talk because you can't really see the audience. So I hope this is interesting. I'm actually very excited, as I was mentioned to Professor Kumar. I sort of took a couple of years away from the deep technical aspects of thing and instead did the VP of engineering and sort of chief architect kind of role, which was a fascinating experience in its own right. But now I'm back in databases. So as Professor Kumar mentioned, I currently work on the company called InfluxData, which is the company behind InfluxDB, and I'm working on a new database engine, which I'll talk about there. I'm also one of the PMC members of the Apache Arrow project. This talk is all about Apache Arrow, more or less, although I'm going to spin it in terms of databases, which often is not necessarily the take things that it gets in. So a PMC member is basically the governance committee there, but I've mostly been focused on the Rust implementation of Arrow, along with something called DataFusion, which is a query engine built on top of Arrow, also in Rust. But I spent 15 years doing C++ programming at places like Oracle and Vertica. I spent a lot of time as a query optimizer and an architect at Vertica. And before that, I was a compiler engineer, and that's actually what I did my graduate work in. So that's kind of me. You can see I'm trying to play down the non-technical stuff, but I've had a wide range of things, but I always seem to come back to databases. So the goal of this talk, by the way, is to convince you that Arrow is a good thing to do if you're going to go off and start a new database. For those of you who aren't familiar, InfluxData is a company that has a specialized time series database. That's what InfluxDB is. So IOX is obviously also which is the project I'm working on, is also very time series focused. But I think what I'm going to talk about is every database system, every data analytic database system, which we'll talk about, not just time series database. But of course, my talk's going to have a time series bent because that's what I've been focused on. So basically, I'm going to talk about my opinions and perspectives of where databases are and what it takes to build one, having done that at least once, and I'm in the process of doing it again. Then I'll describe at a high level, like why you should care about Arrow if you're building a database and kind of what it is. And then, because again, I have no idea what you guys actually want to hear or see, right? I'm going to spend a bunch of time doing some code examples to try to give you some specific, rather than just high level architect diagram level explanations of what Arrow is. I'll give you a lower level, sort of actually show you in practice what it means. And hopefully in that process convince you that if you're going to do this, if you're going to build a database yourself, you're probably going to end up implementing a bunch of what's in Arrow anyway. So I'm going to talk about Rust. Like I said, I did C++, which I believe is what this class is focused on for a long time. Very similar kind of types of languages from a systems programming perspective. I could give a whole talk about Rust. It's actually pretty cool, but I'm sure you can find those online from people who are better than I am. So now I'll put the architect hat on and take a step back and say, well, what has been going on in the database world in the last 20 years? And it's basically been a trend towards specialization. So what that means is, various people have been doing things with different data models. So you'll see databases focused on, time series like, InfluxDB, but also document databases and stream databases and key value database and all sorts of different kinds of databases. Likewise, exactly how to deploy it, especially with the advent of cloud computing. There's a whole bunch of things like Snowflake, right? Recently went public. Their real focus, I would say, was on a different deployment model, use cases, ecosystem, right? Like there's just all these dimensions that new databases are found, which actually means it's a great time to be in the database space because there's lots of great, exciting technical stuff going on. So I think if you look at where this came from, there's kind of like a seminal paper, maybe you've even read it, I don't know, close to 15 years ago now, I guess a little bit over 15 years ago, which was basically one size fits all, an idea who's come and gone. So that was written by Mike Stonebreaker, who's also like the founder of Vertica. So I got to know him a little bit, but he basically argues in that paper, at that time, the primary focus was like Oracle SQL Server. MySQL was just maybe starting to be a thing. And the pitch at that point, IBM had DB2. And so like the pitch at that point was, you just need these one database engine and you don't really need everything else. It's like one size, you can use Oracle for everything. And I think they basically argue that if you did better and you focus on a particular use case, you could actually do like, 100x better. That's basically what, if you want to raise money to go do a database startup, that's basically the pattern, by the way. You should go pick some specialized area, implement something specialized for there. You can show like 100x faster than Oracle probably, and you can raise money, which is frankly exactly what they did with Vertica. But anyway, sorry, that's a decide. So anyway, that's been happening the last 15 years. It continues to happen, right? This is the project I'm working on is this Influx IXDB thing, which is very cool, but I'm not going to spend a huge amount of time with this talking about that. I want to show that one of the key things, if you go read this blog post and others that are related, is that we chose to use Apache Arrow as the core sort of building block of the database. And I'll explain why that is over the course of the rest of this talk. And we're not alone. There's actually quite a few. Sort of Arrow, as I'll mention, has several different types of technologies that are going, well, different things that are part of its ecosystem. And I think if you look around the industry and you look, not that hard, you'll see lots of adoption, both in sort of existing systems, but also new and up and coming systems. It's very popular. As Professor Kumar sort of intimated, right? I talked. This title of this talk is its effect on industry. You kind of got to, if you draw that broader as like not just industry from like the sense of people pay you money, but also industry from an open source projects perspective, it's having a massive impact. And I think the high level reason why they're doing that, again, which I'll explain a little bit more in this talk, is that there's a bunch of stuff that's common to every database, and Arrow basically encompasses a significant chunk of that and lets you innovate at the thing that actually matters for you, not like the basic nuts and bolts that are actually pretty substantial. Before we go into exactly what that might mean for a database system, I wanted to basically make a distinction. I think I'm certainly not the only one to make this, but there's like, I'm sure there's more taxonomy to the database systems, but I basically draw it into two worlds. You've got your transactional systems, right? Whether it's OLTP was the classic name for that, or key value stores is the more modern, similar equivalent, but basically those are characterized by a workload that's mostly look up something by an ID, update it, and it's really about how many transactions you get through per second, and keeping consistency across different documents maybe. And so that's where you've got your classic SQL engines, and you've got Cassandra, DynamoDB, and MongoDB, and all that stuff is what I would consider transactional. And it's not that they can't do sort of aggregates or queries over a large number of records, is that they're designed really for these fast sort of mutations of individual records and have complicated locking schemes that you probably studied to support that. And on the other end of the fence, you've got systems that I would qualify as analytic database systems. OLAP was the classic name for those. Big data, I'm not sure that's the hot name anymore, but that was hot maybe 10 years ago. But basically, the difference is the workloads characterized by looking at large amounts of historical data and computing an aggregate across them, and trying to get an insight there. And the difference, by the way, the reason to draw this distinction is that the way you implement these is very different, typically. And I'm going to focus on analytics for the rest of the talk. That's what IOX is. It's what all these other types of systems are. And I'm not going to talk about like row level locking kind of stuff that you would use for transactional systems. And frankly, Arrow is not what you would want for a transactional system, I don't think. But it's very relevant to analytic systems.
Peter, I have a question on that taxonomy. So I've heard
that
it's a very common taxonomy, OLTP, OLAP. in the database
Yeah.
world. In the last half a decade or so, people are also talking about HTAP, hybrid transactional analytical systems. And
Yes.
there are tools, there are database systems that now actually store 2 copies of the data, one to allow transactions and one to do analytic column stores. Like Times
Yep.
Oracle, I had them visit my class a couple of years ago. What is your take on that? Is HTAP a thing, or do you think the specialization is going to stay because cloud vendors are able to do that? And so, what's your take on that?
Yeah. So my take on it is that the specialization is absolutely going to stay, right? For no other reason than just it's like, if anything, the specialization is accelerating from what I see. It's not like there's like 3 analytic databases and you're done, right? It's actually, if anything, there's a new one like every 30 minutes on Hacker News. I think the problem though, like, but it's one thing to say, hey, you got a specialized engine, but now if you're actually trying to build an application, right? Especially like the kind of stuff I saw in the last couple of years, when you're trying to assemble these various technologies into an overall application, you immediately now will have a problem. Actually, again, the Arrow tries to solve some of this, but like now you have to move data between your because chances are when you're writing a website that does whatever, right, it's probably driven off some kind of OLTP transactional store, right? But then at some point you've got to get the data out of that thing into an analytics system to actually do sort of dashboarding, whatever that your business analysts want. And so there's like, and then people invent Airflow and on all. I'm not trying to pick on Airflow, but there's like a whole sort of ecosystem that gets built up about how to move data and transform it, along the way. And that's like, people have been doing that for 40 years too. Yeah. So as much as people love to kind of pitch you, especially vendors, like, hey, we want one thing that's going to fit all your needs. I think history has shown that that's probably not where things are headed.
So, what's your take on the lakehouse vision then?
The which one?
The lakehouse paradigm that is emerging from Databricks and Amazon and others, where they're saying data warehouses, data science and machine learning tools, all of them can access the same store of data.
Yeah.
Is Arrow targeting that environment because actions be supported in that environment or no?
Yeah, I think if you look across all especially analytic systems in the last couple of years, what they're all really doing is they're switching to storing the data on object store, right? Like using one of these S3 or whatever, actually, and that's what IOX does. And it's a very common pattern. And so then, that object storage system, either S3 or AWS or whatever, like that's effectively becomes the data lake that people were pitching for a long time. And now you have whatever tools that you might want to use, will effectively get data out of that data lake, which is a bunch of files in object store somehow, and manipulate them. And I think realistically what that's going to mean, Arrow is a big part of that, right? It's part of the pitch of Arrow is that this, what you should do, getting ahead of myself here, but like if you have a bunch of data in Parquet files on object store, there's a wide variety of systems that will let you read those. And I think that there's only going to get more, right? So the Arrow vision is that the Parquet on object store more or less becomes the de facto standard for persisted data for doing analytics. And then you have a variety of different engines that are aimed at that.
Sounds good. Thank you.
Cool. So that's what yeah. So now going back to the talk. So if you want to build a new database, I think, and by the way, they were doing this at Vertica, right? I think it's very exciting at first to write something and you play around with it, but effectively what happens quickly is you realize that there's a lot of things you actually need that aren't necessarily whatever is going to make your database special, that people need to actually even like think about it as a database, right? You just like at a high level, you got to get data in and out, and you've got to store the data somewhere. Like we're just talking about put an object store, but now if you put an object store, you somehow have to like be able to find all the files you put there and know what they mean. So you need some kind of system for that. You need a query language, you need a query engine. That's what I spend a lot of my database career on, which again, like none of this is like necessarily earth shattering. There's lots of stuff in the research literature, but it takes time to implement. So, you need a client, right? You need some client API, probably a transport protocol to do it. And the list, I'll talk a little bit more about it in general. So just for perspective, I know how Vertica worked out, right? So Vertica is this analytic database company that eventually got sold to HP maybe 10 years ago. What it was that it was the commercialization of a project called C-Store, which is an academic project out of places like MIT and Brown and some other places. but what they did was they basically made an academic system, used the results of that academic system to raise money. And then it took, I think, a team of like 10 engineers, 2 years to get it to the point where they could run the same queries that they showed in the academic project, right? But in an actual system that like loaded data and didn't have it all hard coded and stuff. So just to give you like some sense, now I think things like Arrow are lowering the bar, but it's still a major effort. So, and again, like none of this is like special to whatever you're going to do to your database. This is just like table stakes to get into the database. So that's why like you used, because they were really, really expensive to do. And here's like off the top of my head, one day I just tried to write out in more detail what some of that stuff would be. And so this is meant to be a timeline between when you come up with a great idea to do a database and the stuff that you perceive along the way. And I'll just give you a flavor. I'm not going to read all this stuff, but like, you have to figure out how you're going to represent data in memory. Like I mentioned, you got to like know how you're going to put on disk and where you're going to actually store it. You have to actually implement the filtering and aggregation operations. Probably you need some way to have multiple people running at the same time with your multiple cores. You need a parser. You need now you got to go implement expressions. You probably have a heuristic query planner. You got to come up with an API. Blah, blah, blah. At some point, you'll discover that date and time expression handling is a nightmare. And it takes you far longer than you ever thought it should or it was possible. But, it is what it is. Joins are also another like shocker to first-time database people. From what I can tell, like you start doing joins, they're pretty straightforward. And then you get a query with like 270 joins or like ridiculous nonsense that I saw at Vertica. And making that work, in a reasonable way takes a non-trivial amount of time. You've got to handle resources. You'll discover at some point that outer joins actually complicate your join algorithm substantially. That was a great discovery at Oracle, at Vertica right before we shipped. We realized we had some bug in the outer join algorithm, but anyway, and blah, blah, blah. So this goes on and on. So like if I was looking at this, I would probably put a pin right about here that like you have to do all this stuff more or less, it'll vary by system, but you basically have to do a lot of these things to get to the point where you'll have something that someone will like plausibly be able to use as a database. And then it's not like you're almost done. You have a lot more work to do after that. Yeah. And you're like, only when you get down there, you actually get to the point where like people think it's pretty good, other than like the first 2 days on Hacker News when everyone's very, excited because it's new, but then after no one's going to use it because it doesn't have enough features. Until you foam in. So the point is, if you look at this timeline, I basically would say that Arrow fills in a lot of these gaps, right? Like it has the basic memory stuff, data types. You don't have to reinvent, how to which kind of integers you want, and doing basic filtering in a query language. Like all this stuff is basically part of what Arrow includes. I put some of these checkboxes as, they're dashed because maybe Arrow is not all you need, but it's a pretty substantial start. So from my mind, what this really does is it accelerates your ability to get something that looks like a database pretty quick, right? And it's not going to solve all this other stuff for you necessarily, but it's going to get you to the point where you can start doing the real interesting work much, much sooner. So that's the pitch for it being a database. So now I'm going to switch, or being a good thing for the database. Now I'm going to switch to like part 2 of my talk, which I'm going to try to talk a little bit about Arrow, the project and the history of it, and like describe what it is and why. So I took this screenshot, I don't know, 6 months ago. And if you go read it, first thing is you'll notice it doesn't really talk about databases anywhere. It says something like it's building a better open source foundation for data science. So if you read that and then you try to connect the dots to database, it takes like, it's a non-trivial step, I think. And that's not, I'm not trying to pick on the Arrow people here. It actually did come out of the data science community, and that's like the primary goal of some of the major contributors. But I think it's much more relevant to databases that is immediately obvious from this. Yes, that's what sorry, I found emojis recently. My daughter makes fun of me all the time for them, but I enjoy putting them on slides. So you're gonna have to see a couple more. What Apache Arrow was, or is rather, it's a project founded by Wes McKinney, who if you talk to him or about him, he doesn't like getting called this way, but so he's the guy who did pandas. And if you know anything about Python or data science, you'll know pandas is one of like the foundational data manipulation libraries of the Python-based data science libraries, like basically all the machine learning libraries. From what I can tell, Python is becoming the lingua franca for all that, or has become almost all of them are based on PAN, where they're to pair the data however they want. And if you look at what PAN is, it's actually a, it's not quite the same, but it looks an awful lot like the kinds of stuff you do in databases. Like it has 2D arrays of, columns, and you're able to slice and dice it with filters and aggregates and join stuff together and all that stuff. So I think if you look at like what Arrow was originally focused on, at least from my perspective, is actually applying some of the ideas out of the systems data science research or database research to the data science ecosystem. Or if you're familiar with pandas, it's basically in memory, which works pretty good for a while, but doesn't work after big data. So whatever these numbers are, right? Like whether they're actually 10 gigabytes or 100 gigabytes or whatever. I definitely saw this, by the way, in my machine learning startups, is that all of those algorithms tend to be in memory, or at least, maybe not theoretically in memory, but all the implementations require the information to effectively be in RAM. So things are great when you've got relatively small data. Pandas is awesome. All the machine learning library is great. As soon as you start exceeding the capacity of your, the ability of a single machine to hold it all in RAM, things get much, very dicey, very, very quickly. And, this is actually, if you look at some of the machine learning startups I was part of, this is actually about where we capped out at the data size limit in terms of, the data set size. And so that meant people had to go down sample or do whatever to actually use the algorithms, which there's still plenty of value to be gotten there. But I think Wes saw, if you really wanted to plausibly do big data or these machine learning and data science applications on actual big data, a much different technology was needed. So this is his slide from some talk he gave 3 years ago. This is like, I'm not going to read this to you. This is like a good introductory reading list for systems, people who are studying systems, right? So this is the kinds of techniques that Wes, as someone coming from the data science background, that he was imagining you could apply to the data science pandas implementations. And he's absolutely correct. So if you look at a lot of what this is, right, this is a lot of types of techniques that are very, very common in database systems, analytics database systems particularly, right? So what they've come up with, and I'm going to explain this in much more detail, is what actually is Arrow. So that there's a memory format, which is a fancy way of saying it's a standard way of making an array of numbers, right? So you don't have to reinvent that. Not only is it standard, it's actually works, and it was designed to work across different languages. So I think that's key, which I'll talk about a little bit. But it's, so just an array of 64-bit ints doesn't sound like it's in need of standardization probably, but Arrow has all of the, you got 64-bit ints, and you got floats, and you got 32-bit floats, and you've got data times, and like maybe if you want to do lists, you got to have a way of storing that. And if you want dictionary encoding, which I'll talk about, you need that. So, I don't mean to undersell this. I'm not going to go into the details of all the things, but it's basically the full featured memory format that you'd end up with in an analytic system if you needed the full type system. And it just has it. It's got compute kernels. Again, like if you're implementing columnar systems, I'm not sure, Professor, if you've talked a lot about columnar, but like my wife would always make fun of me when I was talking about Vertica. We talk about where we're column stores, and so that meant that the data was stored by column rather than row. There's a bunch of reasons why that's good.
Yes, we covered column stores in the previous topic. We covered file organization, buffer management, and all of that. So they're familiar with these things.
Great. Yeah. So column stores, effectively, from what I can tell, are the state of the art in analytic systems. Right. That's what basically all new analytic systems use, and they use it because it's very applicable to modern architectures, right, which have SIMD instructions or some equivalent there that they can crank through. Plus, they tend to compress really well because they've got the same type of data one after another. So anyway, so it's a memory format. You've got compute kernels because once you have like arrays of values, you need to do things like add them together or compare them to each other, and you want to do that in some quick way. There's a file format, a persistence format. Arrow did not, like Parquet predates Arrow actually, but the Apache Arrow project effectively adopted the Parquet file format into the standard, and so now the Parquet implementations are part of the Arrow implementation. Right? It's got something called Arrow Flight, which is a RPC network transfer format. It's basically just a standardized way of sending Arrow arrays across the network. but in a way that you don't have to like copy the bytes all over the place or pack them or marshal them and unmarshal them. And it's also got query engines. So both compute kernels and query engines. Query engine is very interesting to database systems, right? Like thing that takes SQL and actually runs it. A bunch of this memory format, the Parquet file format, the flight implementations, those or formats, those are all standards. I think the compute kernels and the query engines are part of a bunch of the Arrow implementations, like the Rust one and the C++ one, but they're not a part of the standard, which kind of makes sense, right? Because they're not a persistence thing where you would imagine data being interchanged. So Arrow has a bunch of implementations. These are the ones that I looked at. The C++ one, from what I can tell, is basically the canonical implementation, and then it has Python binding. So Python C++ is a very, very popular combination. But then there's a bunch of other language bindings, Ruby, C, R, right? MATLAB is in the process of becoming a thing. And then there's actually native implementations in Java, JavaScript, Go, Rust, Julia, and C#. And those are completeness, but the Rust one's pretty complete, like, which is the one about. So another pitch that Wes would make, or anyone would make when you're talking about Arrow, is if you look at a classic data science application, which that machine learning is, you have a variety of different that you picked because they were best of breed for whatever the particular analysis you were doing or whatever. And then you have a bunch of different systems for capturing the data. Like this is some particular choice of technologies that doesn't quite map to what I used it in some of the ML startups, but it's very similar. It feels very, very familiar, this slide. And the problem is every time you want to go from one to another, you end up having to copy whatever the file format was here. You have to copy and convert to somehow, and then send it over the network and do the opposite on the other end. And so pretty soon you have like the double problem of, not only do you have to have all these different connectors to the different types of systems, right? So that's actually quite a bit of code complexity to manage and maintain, and it's n squared, right? So it's quite bad. Plus you have all the time wasted of copying the same data over into different formats over and over and over again. Huge amount of time wasted, CPU time. So I think the vision of Arrow is if you have the standardized memory model that all these different implementations can use and talk to each other, that the actual amount of effort, both in the maintenance, but also in the actual time spent serializing and deserializing, will be able to be much lower. Right? So this really resonates with me, having gone through the ML startups. Right? Like this left-hand side is terrifyingly pretty accurate, I would say.
Andrew, I have a question here.
Yeah.
The in-memory layout, it's an object. So these systems, their implementers will now have to go and change lower levels of their implementation to talk to Arrow's APIs with some operating system calls. Is that correct?
I think what will actually happen is newer systems will use Arrow natively, and pre-existing systems will likely have one connector that translates back and forth between Arrow and Arrow Flight as their ingress and egress format. So like is Spark really going to rewrite itself to use Arrow? Like probably not. But is Spark going to have a connector that writes Parquet files and reads and writes Arrow, record batches over Flight? I think that's very likely. So existing systems will use probably Arrow Flight as the interchange format here and still have their own native thing. But I expect, if for no other reason, just the simple not having to re-implement the same thing over and over again, a bunch of systems like the one I'm working on myself will just use Arrow through and through and save another copy.
So with Flight, there is still a copy.
It gets copied over the network. What it doesn't do is it doesn't get copied from one format to another, like marshaled and unmarshaled is the big savings.
Got it.
Does that make sense?
Interesting. So some of these new data science systems that are being built. So I don't know if you follow the Dask ecosystem. I teach the Dask ecosystem in my data systems for systems for scalable analytics class, which I taught last quarter. Dask data frames and Dask ML and all these tools, they're building stuff that are scaling the data science by data stack to exactly the middle data regime that you talked about, tens to hundreds of gigabytes. And they still lack data independence. They still lack optimization and all of that, auto-tuning of chunk sizes and so on. They don't seem to be using Arrow. And then there's a project that came out of Berkeley, Modin. They're also building some scalable data frame DBMS. They're not using Arrow. So do you think they should be using Arrow? What's your take on that?
I do think they should be using Arrow, but you have to remember my background and why I might say that. But I mean, in all seriousness, right? Like I looked at Arrow and I said, like, hey, this, I'll talk about this a little more when I talk. But like my thesis was basically, if we don't use Arrow, we're effectively going to re-implement its feature set anyway. So we might as well just use it, hopefully get access to a bunch of the existing community, right? Not have to re-implement a whole bunch of this stuff, contribute back to it, right? Feel like we're doing good, and this overall sort of drive the model. It's not just the implementation, plus you also get access to the ecosystem, right? Like our story for how you do big analytics, SQL, something over large amounts of Parquet files is going to be, don't use IOX for it, right? Go use an existing system that does that great. But since IOX writes Parquet files to object store, like you can pick whatever system you want to analyze those.
Then the next question I have is the generality coming at some efficiency cost? So one reason many of these, so there's two reasons, at least two reasons why database systems vendors have historically had their own proprietary file formats. One is they can optimize it to death for their index features, for their query processes, and so on. Second one is lock-in, of course. Now the first one, do you think there's a loss in efficiency if some of these systems choose to operate with Arrow instead of their own file formats? Or is Arrow's data model general enough to support all of these relations, time series, data frames, and all of these?
Yeah, so I'll answer you with an anecdote from IOX, because we effectively asked that same question. Right? So IOX, a little bit more background, is coming from like the existing InfluxDB data model. It has a particular way of organizing data that's very specific to time series, right? It's like it's custom and it's based off tags and series, and it uses very specialized time series compression. And so the theory there was like, that's about as good as you're ever going to get. It has some downsides, you don't get me wrong, but like it was a customized format designed for the particular problem. In the early days of Parquet, we're like, well, how much worse is Parquet going to be than our custom file format in terms of like being able to compress case format? And I think when we were doing our experiments with our data, we found it was like, if you had tuned Parquet correctly, it was basically the same, if not a little bit better compression than not the high, what was supposed to be a super highly tuned time series database, and so that, or time series file format. So I think that felt really good. And then we did, I was going to say, so then we did a sort of survey of all so that's like the persistence format. We were very happy with the results from Parquet. And we looked at the actual in-memory format. And I think for most of the stuff, like if what you're trying to do is just build a general purpose columnar executor, I think Arrow is about as good as you're going to get. The one place we found that Arrow didn't have a compelling story that actually provoked us to go off and write our own, specialized version of it was it didn't operate on compressed data directly. So it has RLE compression, it has all the data types, it has like all this stuff, but what it doesn't actually do is have some of the more sophisticated abilities to do things like operate on RLE compressed data, which actually I'll talk about. Maybe I'll talk about later. But
okay. Sounds good. Thank you.
Yeah.
Oh, go ahead.
So long story short is I think we found we could use like a vast majority of Arrow, get a lot of value out of it. There's still places we wanted to innovate for our particular use case, but yeah.
Okay, thank you. Let's proceed. Sorry to interrupt.
All right, cool. Yeah, so actually going back to some of your earlier questions, what about all these existing systems that didn't use Arrow? I think the things you'll find is these are also from Wes's slides. They're basically just showing like the Arrow is getting adopted by some of the existing systems, and it's typically used as rather than have to serialize and deserialize the format. Yeah, you can. There's a great academic paper called something like "Give me my stop holding my data hostage" or something, which basically talks about the serialization cost of just like turning data from the internal database format and serializing over the client protocol and sending it to the client. Like that consumes a huge amount of CPU. So anyway, this is like all sort of more Arrow propaganda, just kind of showing that things are going good. It seems to be making significant inroads since it started a couple years ago. Blah 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 blah. The required slide that shows a bunch of company logos that are contributing, but it's pretty cool. It's pretty cool to see the actual community gelling around it. All right, so now what I'm going to do is I'm going to switch back to talking about Arrow as a toolkit for analytic database. Like we were talking about high level sort of industry trends. Like now let's go back to low level code stuff. And so I think if you look at a modern analytic database, you probably need something like a file format for persistence. I'm just pointing out, right? Arrow has that. It's the Parquet file format. You need some kind of in-memory representation. That's what arrow arrays are. You need a way to actually operate on those arrays, which are called compute kernels in the Arrow parlance. But you know, you're going to need that for any analytic database. Probably you need a way to transfer the stuff over the network. Arrow has that. It's called Arrow Flight. There's actually other stuff too that you need that Arrow has, but we'll just keep going. All right. So now I think I'm doing reasonable on time. What I'd like to do is I'd like to switch from high-level hand-wavy architect slides to specific code examples. I'm going to use Rust because that's what I prepare these talks for, and it's what we use in IOX. But I think the basic ideas translate very well to C++. So what I'm going to do is I'm going to show what you would do if you were. And so remember, my thesis is if you're going to go implement an analytic database, you're effectively going to end up implementing Arrow. So you might as well start with Arrow. That's like the primary thesis, and I'm going to try to convince you of. So what I'm going to do, oh yeah, hey, that's even what I said. Good. So in order to do that, I'm going to compare just straight up Rust, which might, like, I don't know how interesting that's going to be to you, versus when you're using the Arrow library. And I think you can just kind of get an intuitive sense of what operations Arrow is actually providing, and then how it compares. I ran these, performance things on my laptop 6 months ago. Please take it all with a large grain of salt. But again, I think the general the numbers themselves not meant to be super accurate. I think the trends though are legit. In order to explain these examples, please permit me just a few minutes to talk about this stuff thing called the InfluxDB line protocol. It's basically like a CSV file, except it's basically a way of describing columnar, 2D columnar database data with columns and rows. The difference is it actually makes distinctions on certain types of rows. So, or certain types of columns rather. It's not hugely realm. You just think about this as a CSV with like some extra stuff, but so it's got measurements, it's got tags, which are name value pairs. It's got, these are called fields, but these are, again, columns, right? Temperature equals 82, right? That's a column with numbers there. Here's a column of more numbers, and then this thing is a timestamp, second precision timestamp. The way that maps to, I'm calling it IOX, but you can think about it as any general purpose relational model, is you've got the weather measurement is the weather table, right? So this is the table name. You've got this location thing, these tags as a column with data. You've got all the fields also as columns, and the timestamp is also a column. Does that make sense? So it looks basically like a four column table. And yeah, we're going to spend a bunch of time looking at this location one. So that's important. And this, by the way, shows up a lot in the IOX specific use cases. So these are called tags, right? So in this case, it's like you're getting maybe metrics data from your data center. And the reason this is important is because these are strings, but they're also low cardinality, which means there's not all that many distinct values, right? Because there's not that many data centers, right? You might have millions and millions of points a second coming in, but you only have like 30 data centers, maybe at most. So yeah. So in fact, let's use that as the motivating example of what we're going to do is, if you're writing a database system, you might imagine that one of the key things you might want to do is, aggregate over rows that pass a predicate. So we're going to pretend like we're finding all the rows that are not in US West, right? So that's whatever, I just made up some data center that's called US West. So the first thing you need to do is get the array. Here's how you might do it in Rust. I'm not going to pretend like I'm going to do a great job explaining the Rust syntax to you, but basically this says go through 0. I think it's 10 million tags, right? So some number, and it just says for each one of those numbers, right? If the number is has a remainder of 0, you get this string. 1, you get that string. 2, you get that string. So it's making however many rows this is with 3 distinct values. Every third one is it repeats. Hopefully that makes sense. And it gathers them to a vector. So that's just an array of strings. And those are like they're the exact same things like C++ std stir in the sense that each one has its own allocation. So yeah, I did this on my laptop back in the day, and that was 10 million elements, and it took 600 milliseconds. Here's the equivalent way you would do it with Arrow. There's actually probably better ways to do it, but here's one way to do it. I don't think the syntax is particularly important. I think if you look at them, they're approximately the same complexity, I would say, right? You're basically doing the same thing, going over the range of numbers. For each one of those numbers, you're deciding, which one of the three items you're going, and then you're calling append value. So if I did that, the same number of elements, it actually turns out Arrow made it much faster. And that's not because, there was something stupid about Rust or that Arrow is like doing crazy things. It's just internally, the default way you do this vec of strings in Rust is an array of allocated strings, right? Which each one of those strings themselves has an allocation for the actual string content. Right? So this, I don't know how your database implementations went, but like you'll find as soon as you start dealing with strings, what you do not want to do is make an SCD string for every string value, because that is ridiculously slow. And so, Arrow knows that, and instead of actually making individual allocations, it makes one big allocation, appends all of the string data back to back, and just records the relative offsets. So, again, yes.
And the question, sorry again, I see.
Yeah, no, go ahead.
Questions. This is very cool. Quick clarification. Is this single threaded?
Yes.
Okay, this is single threaded. So the dot enumerate
single thread, single core.
Are they natively parallel in Arrow for multi-core?
No. This is a Rust thing. That's for each and enumerate. This is Rust, and those are the non-parallel versions. There's a variety of like libraries that might let you do this stuff in parallel, but
got it. Okay, so
in this case, it's a single core.
Okay.
Yeah, all these numbers are single core. There's no multiple thread, no multi-threading at all. All right, cool. Yeah, so this is how you build the array. And again, like it's not like if you actually went to build a database in C++ that you're going to use vecs of strings, right? Like it's not how you're going to do it, but you're going to have to invent something like that Arrow already has, right? Where you store all the data next to each other, store offsets into it, minimize the allocation cost. All right, so let's look at memory footprint. I don't think this is at all interesting unless you're into, depending on how interested you are in functional programming, sort of Wieneism. But anyway, this is how you in Rust would go sum the size, maybe the allocation size of the string. It probably undercounts it because this SLN, there's probably some buffer slop, but whatever. It basically is the approximate size. And you find there's, whatever this is, 320 megabytes. If you remember, there's 10 million elements. So that's like 32 bytes per element, which is entirely due to the overhead of these string things and whatever allocation overhead. You do the same thing in Arrow, and actually you find that the allocation is much less. Again, this is all due to the overhead of the string structure. And if you're actually implementing something in Rust like this, you would not use a string like this. But I'm just, the naive way is doing a string, and the naive way of Arrow just does the right thing. So far, so good. Okay. And again, remember, my thesis is just trying to convince you not that Arrow has amazing new breakthrough techniques in it, but that it is sort of represents best of breed state-of-the-art columnar execution and execution techniques. All right, so if you remember, my example meant to be, we're going to go find all the rows that aren't in US West. The typical way you do this in a database is you would go scan all the, especially in a columnar database. Like one of the things about analytic databases is you typically don't have mutable storage, and so what you actually do is you'll have an array that you never change, and you go compute things based on that and make a new array. So that's how this will work. The high level pattern is we're going to go make a new array, a bit set, right, a bit vector, where it's effectively logically an array of true false values, and it'll be true wherever the predicate passed, right, where the row should pass, and it'll be false 0 elsewhere. So this is how you would express that in Rust. Again, this just makes a vec of bools. I believe Rust does the same sort of trick that C++ does. If you have a vec of bools, it turns it under the covers into a not actually 8 bytes one after another, only using a single bit, but it like does bit packing, but whatever. So the point is, this might not be as bad as you might imagine. This just runs over all the strings, evaluates the predicate, makes it into a Boolean bit vector, and then in this case, I'm just counting all the places where that predicate evaluated to true, evaluated to 1. So in this case, it runs in 50 milliseconds. Here's the equivalent way you can do this in Arrow. Just showing you, right, we built this array thing in our last example. And there's a specialized, this is what I was calling a compute kernel, right? This in particular, this one is not EQ UTF-8 scalar. So it basically compares an array to a scalar value and finds the rows where it's not true, or where that array is not equal to US West. And then here's, you count basically the same thing. And actually, if you look at this, interestingly, this actually is slower in Arrow, right? Which might lead you to conclude you should just be doing it in native Rust and not messing around with Arrow because it's slowing you down. But I think you need to look a little more carefully at this example. So you'll notice here, this filter talks about, I don't know, whatever, blah, 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 V, not true. This has some V. So some is a Rust thing. Some are known as the way to represent effectively nullable types. So it's a fancy way of saying that, I'm not doing a great job explaining it, but what effectively this right-hand side handles nulls is what I'm trying to say, right? So this is actually, if the array might or might not be nulls. This is, by the way, something else. If you're going off to implement your own database, you'll discover sooner rather than later, and it'll be probably an unpleasant surprise, is that handling nulls actually is quite, like, it consumes far more time than you would ever care to admit. And it's like really important to get right, but it's just like, I don't know. It ends up consuming much more time than you would imagine. And it's like, you can get it working pretty good. And then all of a sudden someone asks, well, what about null? Or like, what does null equal null? And I don't know. I spent 4 years of my life dealing with nulls and arrays and that sort of stuff. Yes.
You're saying Arrow's operators can support null value ternary logic?
Yes. I'm saying the kernels, well, depends on which kernel, but yes.
Got it. So they do support ternary logic. Interesting. Because that is important in the database world.
Oh, yeah, it's huge.
Okay.
Yeah, and it's something else I like glossed over too, but the arrays, I'm talking about just as arrays, but they're more than just arrays. They're arrays, and they also have an optional validity bitmap attached to them, right? So it's effectively, the arrays can have built in the ability to represent null rows.
Got it. Okay, that's great.
Again, it's like, it's not earth shattering, but it's like, it's very important when you're dealing with real data.
I think data scientists, when they deal with data frames, they often run into semantic issues with null handling. And that's a perennial problem for data frame APIs. And one of our assignments in that previous course that I mentioned involves null handling. And so it's great that Arrow is actually supporting this here. One last question, again, going back to the parallelism question, you're operating on collections, you're operating on arrays, so they can be natively parallel, right?
It could be. I think, at least the way I've seen them implemented, like if you're doing this way, is you'll typically break your data into, Arrow calls them record badges, but they're basically horizontal slices of the data. So like maybe 1,000 rows or 8,000 rows at a time. And so then your unit of parallelism will be, you run this kernel thing in a single core, but you run, each array has 8,000 rows and you run a whole bunch of arrays in parallel.
It's a shard-oriented parallelism.
Yeah, and I think that's actually kind of the canonical best practice way. If you want a vectorized execution engine, like that's effectively what you end up doing. You end up vectorized execution engines. You take a block of data and you run the same thing in the same core because it's super fast, right? And you do that as much as you can in parallel.
What about hardware level, instruction level parallelism, like the stuff like bit weaving, stuff that Oracle and SAP have explored? Is that possible to be integrated with Arrow?
Well, Arrow does SIMD. Well, at least the Rust kernels do SIMD, which I'll talk about in a little bit. I'm not actually familiar with the techniques you just described, so I'm not sure.
Okay, we can sync up on that later. So there's some of these database vendors have done hardware software co-design kind of stuff, and they have exploited all the way down to instruction level parallelism and other stuff on the processor itself. And this is part of the reason I was asking the specialization part. One of the reasons they did that was they control all this all the way down to the hardware. Like Oracle even came up with new ASICs for their operations. I don't think it really took off that much. I don't think people use ASICs for SQL, but it is possible. And in the data science world, because people are starting to use GPUs and ASICs and so on, there is a possibility that they might want to use more hardware level parallelism. So that'll be curious to see how systems that choose to use Arrow interface with those sorts of processors in the future.
I'm probably biased, so like I can tell an anecdote from an earlier part of my career is that I worked as an XSLT, which is probably like some ancient technology for all you, but it was some XML to XML transform language. And a part of that system was a XML parser, whatever. And it was hand coded in C, and it was it was actually really cool. It was kind of grody if you looked at it, but like it was ridiculously fast. And actually, one of the things our company tried to do was build a custom ASIC to do XML parsing. And it was like, it turned, remember, I'm on the compiler team that owns the software part, right? So I'm biased here, but like basically the software parser was much faster than the hardware parser in almost all of the cases. Like unless you actually were able to send massive XML documents to this thing and you kept it fully occupied, like the software parser actually would just beat it. Oh, and like every year you get an upgrade of the Intel chip and all of a sudden it'd be like 10% faster, which is pretty good, which was not the case with the ASIC that we were working on. So, from that, and the reason, by the way, that it was slower is not because the ASIC sucked. It was because the time to actually parse XML ended up being dominated by the time to send it to the card and get it back rather than actually useful work.
Sounds good. Okay.
But anyway, sorry. So I'm not super convinced that custom hardware is where the industry's headed, but it's cool. But
arithmetic intensity depends on the arithmetic intensity of the operations. I think the parsing stuff probably doesn't have that much intensity. Aggregations may have more intensity, but even the database operations, the A-frame operations, if you look at the roofline plot, they don't have that much intensity. We're not talking about deep learning here. So even here, I am also skeptical whether accelerators are going to be helpful.
Yeah, well, the modern x86 chips are just really, really good. And they're like, you can get 32 cores on them that are really fast and they have crazy memory bandwidth. And that's where the data's got to end up anyway. So like, it's really tough to beat that. And they've got this crazy, economies of scale going. So
there's research in the database systems world and in the intersection of computer architecture on exploiting GPUs for relational queries. They have actually come up with mechanisms to avoid exactly the problem you mentioned, which is the shipping takes longer than usual. And this basically means you build a memory hierarchy that occupies the GPU memory caches and stuff like that in a more sophisticated manner to avoid round trips to DRAM. But I don't think people are doing that just yet for some of these things. We'll see how it goes. Okay, let's continue.
Yeah. I think for custom database systems, it makes sense that like if you're building your own custom app, then you can basically have control over the hardware, which is basically describes most modern cloud systems. It's not unreasonable to imagine you could actually take advantage of GPUs. But even like, again, going back to the machine learning startup I was at, like you want to use GPU accelerated algorithms and actually turn it to be a big thorny question of like, well, do we assume they have GPUs? Like, can we require that the customers have GPUs? And the answer, of course, is no, right? Or like, anyway, so that means you still have to basically have the software complexity of like the GPU version and the not GPU version. So anyhow, sorry, let's go on. Yes, so if we go back to my this example, I was starting to hint that the right-hand side doesn't have null handling, or that the right-hand side just handles null, whereas this left-hand side doesn't. So if you actually take this example, again, I'm sorry for like this Rust sort of vomit at you if you're not into Rust. This functional style took a long time for me to become at peace with, and actually now I appreciate it, but I did not appreciate it initially, especially coming from C++. But effectively, here's how you would represent something similar to nulls in Rust. And what you do is, rather than a vector of strings, you have a vector of things called options of strings, which option either has a null or a sum, and then there's a bunch of support in the Rust standard library for that. So again, not that I think it's important for you to really understand the details of the left-hand example. What I think is important is, so it's still pretty fast. But I think what's important is like, hopefully you'll agree, this left-hand side is quite a bit more complicated than the last slide. And again, this is like one function call in Rust, right? Yes. Oh, by the way, I should also tell an anecdote about this thing. I presented these slides. This is like 3 months ago. I haven't updated them yet. And like 2 days later, some guy in the Rust mailing list had basically put up a PR that made the performance equal to the native Rust one. So anyway, although I think it makes a better story saying that it handles nulls. Anyhow, moving on. So now we've gotten, we're doing our little database coding thing, and we've gotten to the point where we found all the rows that aren't in US West. And now what we're going to do is we're going to actually do something with them, right? So the way these columnar systems tend to work is you get the array of input data, you evaluate the predicate, typically you evaluate a bunch of different predicates potentially. And so that's why you'd have a bunch of vid vectors, you eventually add them all together to figure out which rows pass. And then if at some point you typically will have to materialize them, which basically means copy the rows that pass the predicate from the input to some new intermediate output. So that's effectively what this code does in Rust, right? So this is the thing, the array that has all the rows that matched the predicate, and it runs through and it does this filter map nonsense, but effectively it finds the strings that match and it copies them. That's what this clone does. So it's literally doing a string copy. This is the same thing you do if you use a copy constructor on the CSED string, which, at least Rust, one of the nice things about Rust, at least forces you to tell it that, yes, you're cloning the string rather than just have it auto-magically happen when you write string equals string. Anyhow, so that's what you do. This makes some number of strings 450 milliseconds. If you do the same thing in Arrow, it does the same story, but it's much, much faster. And that's because, well, for several reasons, but because it's effectively doesn't have to do this cloning is why. And it's just copying around the indices that passed. So I don't have pictures that show it, but the illustration is basically the Arrow array of strings isn't actually an array of strings. It's an array of pointers into a buffer that has a bunch of strings in it. So this operation is not actually operating on strings. It's operating on all those offsets. And then the underlying buffer is the same. And since it's immutable, it just gets shared. All right. So I hope this makes sense or is like marginally interesting to people. Next thing, now I'm going to switch to something else, which is more efficient encoding, which in this world means dictionary. So, if you're hip in the back of your head, like, man, I was building a dictionary or I was building a database and I had this data model that Andrew described a couple of slides ago of like 30 different data centers, but like millions of rows a second, right? I would not be representing those data centers as strings, probably, right? Because only 30 of them, I probably know them up front because I don't add data centers all that often, whatever. So it actually turns out Arrow already has a story for that. And so the canonical thing, again, this isn't like something Arrow invented, but this is something that I think Arrow sort of took state of the art and made it a standard, is to do, it's called dictionary encoding. And it's very simple, is that rather than having a single array, it's actually, I won't go into it. So, it effectively has a dictionary array of strings. Again, this isn't actually an array of individual strings. It's an array of like indexes into yet another buffer. But so logically though, you have a dictionary with 3 distinct values here. And then rather than continually repeating the same string over and over and over again, you just store which location in this dictionary belongs to. Right. So in this case, it's 012, standing for US East, Midwest West, and just repeats, right? That was our data sequence. And so in that case, you can store as U8. You could store even smaller. In Arrow would store, I think U8 is the smallest you can get away with an Arrow. But that's starting to sound really, really pretty good. And here's the Rust code that actually does that with a string with Arrow. I don't really expect that you'll remember a couple of slides ago what this looks like, but basically it's only the setup that's different. This part's basically the same, and it's only sort of setting up which of these builder things you use is different. So that's actually kind of cool, right? Without doing a whole lot of extra work, you can get the value of this dictionary encoding. And in this case, it's something stupid, right? Like rather than 320 megabytes, it's 10 megabytes. And that's simply because rather than storing 10 million strings, you're storing 10 million bytes, which shockingly is quite a bit slower, or rather is quite a bit less pricey. It still takes a non-trivial amount of time to build this, by the way. And that's because as you're building a dictionary like this, you've got to actually look up each one of the input rows. You've got to figure out which dictionary entry it corresponds to. And there's no particular fanciness that I did here. So effectively, each one of these appends has to do some kind of hash lookup thing. But that's still pretty good, right? Basically the same code, much more efficient. All right, so getting to the close, I know this is like probably just way too much stuff, but let's continue on with our hypothetical example of creating a new database. And you probably will read about SIMD, right? Single instruction, multiple data. This is the trend in modern hardware to use all these fancy transistors they're getting, right? It's not to make the clock speed faster. It's actually to end up providing operations that operate on multiple data at a time, right? So this is actually very one of the reasons why columnar stores and columnar architectures are very common in the analytic world, is because of the availability of instructions like this on modern CPUs. So basically, at the high level, if what you were going to do is you were going to compare the left and the right, the green and the blue arrays, and just say you're going to find all the elements where the green one's greater than the blue one. Like that's effectively what we're doing. With SIMD instructions, depending on exactly what's available on your processor and the width of these data items, let's just say in this example, you can do 4 at a time. There's basically a single instruction that you can pass to the hardware, which will compare all 4 of them at the same time and put the results somewhere. Right. So in order to take advantage of that, oftentimes the compiler would do this for you, if you're lucky, or you can write code that uses the SIMD intrinsics yourself. It does pretty good. You do blocks of 3 in this case, or 3 blocks of 4, and then you have to sort of have some special logic to handle the remainder case. Again, I'm sure you're all capable of actually writing this if you sat down and thought about it. However, it's kind of cool that if you just use Arrow, you get this for free, right? Like someone's already thought about this, they've done this. In this case, this is the kernel greater than, and left and right are 2 arrays, right? So in order to compute this output array, this is how you call it an Arrow, which I thought was pretty cool. Not because, if you were going to go implement this yourself, you would probably end up with exactly the signature. It's just kind of cool that Arrow did this for you. And just to give you a sense of what that actually looked like in Arrow, when I copied this from the code base 6 months ago, this is it. And again, like I'm probably not qualified to go through this, but you can kind of see, right? Like it has T range, right? That's how many SIMD sort of parallel units that you have available, and allocate some size for the result. It goes through by the number of, basically makes steps to get those 4 at a time, and then it does some remainder cleanup logic and eventually assembles the result. But my point is, you can write any of this stuff if you use Arrow. That's basically the point. Yeah. So again, I could just, I probably hit this over the head too many times, but as you go through the process of implementing a database, right, you just find over and over again, like there's just stuff that doesn't really add any value to your database, but it's just required for the database to be treated like a database. Like you got to support nulls, for example, right? Like even though the first implementations when people do these, like invariably do not support null because they don't understand why it's important, and it complicates things a lot. And you have to handle other data types, right? Same story. Like, no, I got to handle timestamps. Well, crap, right? Like that's all. It's like everything worked great when I had ints. Now I got to do something fancy with timestamps, or maybe I got to handle floats or float 32s or whatever. It's not like hard theoretically, but the practical implementation of doing it turns out to be substantial. And you've got to do vectorized implementations. You got to put it all in stores and over there, blah, 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 blah. Well, you got to make sure that it actually talks to other systems people care about. Just huge laundry list of stuff that I think Arrow gives you a big head start on. Of course, if this was like a history talk, I'd probably use this time to pitch you to either come work for us or to co-contribute to Arrow, both of which, of course, are valuable things to do. But since this is an academic talk, maybe I'll just end it there.
Great. Let's see. Thank you, Andrew. Let's see if we can, wait a minute. There's no clapping reactions on the non-verbal. I'm sorry about this.
Yeah, I know it's tough.
Thank you again for the nice
No,
I think students are not able to click the clap button either, but we appreciate you showing up, and they put clap.
Yeah, Zoom's always tough with like just a bunch of
they put thank you and clap on the chat. So thanks also for the code walkthroughs. That were very helpful, because this is an implementation class. They do C++ implementations of buffer manager, and they look through the file formats and stuff. Also B+3 index, so they actually go into the nitty-gritties. It's nice to see Rust. I've actually been meaning to learn Rust myself. It's been years since I picked up a new programming language, and Rust seems like the best candidate to pick up. Let's see.
Frankly, we're using Rust because it's what our CTO at InfluxData wants to use. Like, when you're starting, like that's, if I'm honest, like that's just the reason. And but it's grown on me huge amount. Like it has a
good things. I've heard a lot of good things from multiple people, even in academia, about Rust. Okay.
I think it's got this huge learning curve, but once you get over the learning curve, it's.
I see.
anyway, I don't know. It's definitely worth doing. That's my suggestion. All right. Sorry. What was the question?
So questions from the audience. Students, if you have any questions, feel free to post on the chat or raise your hand. Supun has a question. Supun, would you like to unmute and speak? Supun?
Okay, maybe.
Oh, go ahead, Supun.
Can you hear me?
Yes, we can hear you.
Okay, so my question is, so when you have a big data pipeline, maybe as, for example, you showed the operation where you do the comparison, and it's possible that you have a series of operations like that.
Yep.
Can Arrow do some like operator fusion style optimizations where you fuse these operations to do together so that you can like avoid like reading writing from the memory? And more generally, like I would like to know whether is there any plans to support like auto code generation for a given plan, or do you expect there will be some opportunities for that kind of optimizations in the Arrow based database?
Okay, cool. So let me spend a few moments explaining what I think the question is and answering, and then I'll answer. So typically a predicate won't just look like in a database, in like a database context, a predicate won't look like just a single column is not equal to some value, right? Which is what I presented. Typically you'll have the predicates not equal to some value and some other columns not equal to something, and time is greater than yesterday plus 5, or like whatever, right? So you get some non-trivial operator tree. And so there's, from my summary is, there's two state-of-the-art ways of evaluating that type of tree quickly. The first is, I think what you're describing is operator fusion, right? Or it's basically compile down use some kind of just-in-time code compilation technique. LLVM is very popular in order to actually compile that expression tree into a single sort of binary thing, which can evaluate the expression in one go using compiled code. So that's operator fusion. And then the alternate strategy I would call vectorized execution, which is effectively what I presented in these slides, where you evaluate a large number of rows at a time. You evaluate into an intermediate buffer. And both of the techniques are basically designed to avoid the overhead, right? Because if you effectively implement a naive implementation where just like for each row you go and evaluate this expression tree, and then each row you go evaluate the expression tree, effectively what you'll find is, like, without thinking at all too hard, is that the overhead of actually traversing the expression tree like ends up dominating all the actual computation you're doing, right? So that's, I probably should have started there. Like, so state of the art is there's these two techniques, and there's a paper, I can't remember what it's called, but it's something like All You Ever Want to Know About Vectorized Execution or something like that, which is a cool reading that basically describes these two different techniques. And their conclusion is they're basically both really good, and there's certain cases where one's better than the other, but you can do pretty well with both. All right, so that's like the theoretic story. So now the actual answer to your question is, in the C++ and Java implementation, there's something called Gandiva, and there's the start of an expression evaluator that's based off code generation. So in C++ and Java, I'm not an expert in those language implementations. There is some version of a code generator that does expression code generation. In Rust, there's not, and I don't know of any. I'm sure people would be interested in if you wanted to prototype that out, but there's not one to my knowledge. And to be honest, like, given my background, like, there was especially given the academic paper, like, that was effectively our finding at Vertica too, which is the vectorized execution method is pretty good, and whatever overhead you have for like evaluating expression trees can be very effectively amortized by doing vectorized execution.
Okay, thank you.
Welcome. Yeah, thanks, Supun. More questions from the students or the audience? Yes, Sai, go for it.
What do you think are the biggest limitations Arrow has currently?
Yeah, so I think the biggest limitation is that it doesn't have, technical limitation, has no way to operate on compressed data. And so, like, I think Professor Kumar and I were kind of chatting about that earlier. It's like there's a whole subsystem in IOX that's designed to actually be able to operate on compressed data. And in particular, RLE compression is a very common, popular one if you're like, if you think about the data I described as being really common in time series problems, and it appears in other areas too, not just time series, but I happen to be very focused on time series right now because that's what IAX is, right? You've got these very low cardinality, they're called tag columns in the Influx parlance, but they're basically, but they appear in lots of other places. They're just low cardinality strings, right? Because they're like some identifier, their tag value or something, or labels or whatever. And a technique that works really, really well on those is run length encoding. So you basically turn, especially when you dictionary, you like basically turn them into dictionaries like I described, and then you run length encode the dictionary entries. Because oftentimes what you'll find is like the same value, like US East, is just repeated like 1,000 times. And so rather than repeating the same integer value 1,000 times, you put like integer 0 repeats 1,000 times, right? Integer 1 repeats 1,000, repeats 300 times, whatever it is. And so you can get extraordinary compression ratios. Plus, I know it's kind of hard to absorb what RLE means just when we yabber at it, but basically operating on compressed data can be very, very effective is basically the conclusion. And pretty much all the fast column stores have some version of operating on compressed data. So, because the alternative is you basically have to expand the data out from its compressed form into some very inefficient form because you repeat the same thing over and over again. They just typically filter out almost all of it eventually. So if I was going to say what's the biggest technical thing I've seen that's lacking in Arrow, it's that there's no way to operate on compressed data. And I'm not, to be honest, sure where that's going to go, because one of the key sort of tenets of the Arrow memory model as it's currently described is that you're able to go in order one time to any particular element in the array, right? Which basically rules out pretty much any kind of sophisticated encoding scheme because you basically need direct O1 access to any element in an array. So in IAX, we basically chose we're going to go build our own customized version of some subset of the Arrow functionality that can operate directly in RLE compressed data. It's called the read buffer if you ever look at our stuff. And at least in my mind, the reason for that not using Arrow is because Arrow doesn't, like, we just can't operate on compressed data, and it's so important. And by the way, there's a whole other like survey paper talking about various different encoding techniques that you can use other than RLE, but RLE is very important.
Okay, we have another question from Weil. I hope I'm pronouncing your name right.
Yeah, correct.
Yes.
Yes. So my name is Weil. I'm from UC. I'm not from UCSD. Just like got an invitation. Thanks to Professor Kumar. So my question is about the integration between Parquet and Arrow. So I know Parquet has the dictionary encoding. Is that like once I translate from Parquet to the Arrow, is that I'm going to import the dictionaries as well from Parquet, or I have to kind of like decode and then encode again in Parquet?
I think the short answer to your question is the implementations of Parquet and Arrow typically have to decode and re-encode the arrays. But you as a user, if you use the Rust library or the C++ library, you typically will just open a Parquet file, and there's parts of those libraries that are implemented that will read them out as Arrow arrays. So like from a user perspective, you don't have to do the kind of manipulation you're describing, but from like under the covers, it has to do that. And there's a variety of reasons for that, not the least of which was Parquet predates Arrow. I mean, there's actually a bunch of challenges. Like if you look at Parquet and Arrow, it's clear they weren't designed together. Like the data type models are different. So like the logical, there's not that many physical data types that people care about. It's like 64-bit ints and 64-bit floats and like strings and byte things. But the logical types on top of that, like what makes a timestamp or like how you represent signedness and endianness and stuff, like that actually turns out not to be the same between Arrow and Parquet, which is very annoying to say the least. But yeah, and also if you look at like the way Parquet is actually it's a very impressive file format if you look at it in detail in terms of like how good it is at compressing, and they play all sorts of tricks. And so the dictionaries themselves are not like, they're not just arrays, like they themselves have some very sort of sophisticated encoding that you have to decode first and then use them to sort of as you're streaming the data through. And you can do things like I don't know, it's probably too much in detail, but you can end up with like multiple dictionary entries. Well, no, that's not true. Never mind. I don't want to talk about it. Okay, sorry. It's a bunch of complexity with actually dealing with the data in the actual Parquet format that, yes.
can I maybe ask another question, if it's possible? Yeah, so the other thing is actually the input and output between operators. Is it going to be like a batch of pointers?
Yeah, that's effectively what it is. It's yeah.
So how is that going to be like in terms of memory alignment, if we're going to like on SIMD vectorizations?
Yep. So that's part of the Arrow spec, is talking about the alignment of the memory, right? It depends on the width of the data type and the architecture, whatever. But basically, the Arrow arrays are designed to be aligned on the appropriate word boundaries for whatever data type they store.
Thank you.
Great. Thank you, Well. Anyone
And
else?
I mean, that's another great example of like something you'll eventually end up having to deal with if you're writing a database, but like you just like someone already thought about it there. You just like, fine, just align it the way it's supposed to be, and it's all good.
And that's the sort of nitty-gritties that people often results in bugs and stuff. So it's nice to have a standard that you can outsource that to.
Yeah, well,
so
what'll typically happen is you'll implement something without alignment, realize you need to align stuff, go back and try to retrofit alignment back into the code, and that retrofitting will often introduce bugs because like you just weren't as, because whatever, you weren't thinking about it initially.
Questions from the students? These are all great questions. So I have one last, or maybe two last questions. What is the implication for non-volatile memory? So Arrow is an in-memory storage format. What happens when we move to Nvram and the disruption that it causes to database systems architecture? And the second question after that is, the business incentive for lock-in is very strong in the database industry. I know there's a SQL's ANSI standard and stuff, but every DBMS vendor has their own dialect. That means it's impossible, almost impossible. It's very painful to port an entire enterprise application from one DBMS vendor to the other.
Yes,
why do you think that incentive will not exist in the data science landscape if and when these companies start commercializing these sorts of tools?
All right, well, I'll answer the second one first. I think it's basically because they can't get away with it anymore, because there are standards like Arrow that customers effectively will demand out of the vendors. Like that's the short answer, right? And we'll see, right? But like, if at least when I was building enterprise apps at these ML startups, or you saw what they were doing at Vertica, typically what happened is like the engineers would basically go prototype something with, like, you're effectively trying to build them with big open source communities, right? So like a lot of those vendors will start as open source, and like it's going to be a non-starter, right? If you have some open source product that uses some weird proprietary format, like the engineers aren't even going to like think about that. So you basically need to use the standard formats to get them into the pipeline, even get them considered for inclusion in the overall apps. Yeah, so I think it's just that, with the advent of open source software, they're just not going to be able to get away with it. Yeah, the SQL spec, by the way, it's fascinating to read. If anyone like don't actually read it, wouldn't be my recommendation, especially because it was effectively retrofitted after the fact, right? Like Oracle had an implementation, IBM had several, like one or two already. They thought they could make a standard. They made a standard, and it's like, yeah, no one implements the standard fully. Like no one, none of them. So.
Okay, that's interesting. Let's hope that is true, that customers actually demand it and the data science landscape stays open. So coming to the previous question about the non-volatile memory and Nvram and stuff, what's your take on that?
Yeah, so Arrow has a way, like a serialization format, to effectively serialize Arrow arrays into, byte streams, which is what you would effectively need for Nvram. It's not clear to me that like Arrow is not the most, it's like just yakking about not being able to operate on compressed data, right? Like there's plenty of data that it's not particularly great at. But to be honest, I'm not sure where in sort of the IO bandwidth sort of cost trade-off Nvram fits between, like, yes, you got big main memories, you've effectively got the infinite FTP server in the sky with the object stores, right? Super low cost, relatively high transfer cost. Nvram's going to probably sit somewhere between there, and like you've also got locally attached storage potentially. So yeah, I don't know. It's hard for me to imagine Arrow being a great format to actually serialize in some sort of relatively expensive format, because Parquet is so good, right? And that's something else I should point out about Parquet and Arrow in general, and the readers, is that Parquet is designed so that you don't, like, if you've got a million rows in there, it's designed so that you don't actually have to decode all million rows, right? And you can see that in multiple different ways. the first is it's actually columnar, right? So literally it's like physically the different columns are stored separately, but it's also designed to have, it has what's called row groups. So you don't just write the single column the whole way down, you write it in horizontal strips, and each one of those strips can have its own statistics. And so, you know, the very first thing you'll do as a database vendor, if you're reading Parquet files, is you look at those statistics and you'll skip whole row groups if your predicates can't match them. And so, not sure where I was headed with that. I guess I'm like with proper setup of Parquet files, it's actually pretty efficient. So yeah, I'm not sure. I don't know.
That's fine. I think these are sort of open research questions that I'm also curious about in the space. There's a lot of activity here. Even in the cloud native regime, they're starting to build hierarchies of caches. Of course,
Yes.
We're reading it from blob object stores, but there's caches built in
Oh, yeah.
levels, and operators are being pushed down closer and closer to S3 as well.
Mhm.
And there's a lot of activity. So it'll be fascinating to see how the space evolves. I think we can stop the recording here. So thank you again, Andrew, for visiting us and for all these insightful Q&A.
Thank you very much for inviting me. I enjoyed it.
And the recording will be stopped now.